Section 15.4, Green's theorem. So let's start with a theorem. Let R be a simply connected region with a piecewise smooth boundary, C. Oriented counterclockwise. Okay, so that'll be abbreviated CCW in the future. Oriented counterclockwise. Okay, so that is C is traversed once. So that the region R is always to the left of the curve. Okay, if M and N are continuous first, have continuous first partials, on the region R, then the integral over C of M dx plus N dy is equal to the double integral over the region R of the partial of N with respect to x minus the partial of M with respect to y dA. So we can turn our line integral into a standard double integral over some region R. All right, so let's break this down just a little bit. What it's saying is that if I've got some simply connected region R, so maybe something like this, okay, so simply connected means there's no holes in it, it's not two separate disconnected sections, okay, this is it. This is my region R. Then this is C, and we're moving counterclockwise around this curve. So if you were a person driving a car along this curve, and R were like a mountain range or something, those mountains would always be to your left. That's the idea, okay? So we got to go around this thing counterclockwise. This is simply connected. Let's see. R is simply connected, just meaning, like I said, there are no holes and there are no gaps. It's, you know, there's not two separate sections. No separate sections. Separate, right? Separate sections. Okay, it's all just one smooth continuous piece. Okay, and C is going around that in a counterclockwise direction. Okay, now because C is a closed curve in Green's theorem here, a lot of times the line integral over C is denoted with a little circle in the integral symbol. So often, just to be aware of this, especially in a physics course, you'll see this all the time. Often, because C is a closed curve, we can denote the integral as the integral over C with a little circle in the middle of the integral symbol. Okay? All right, so let's do an example of Green's theorem. All right, let's evaluate the line integral using Green's theorem. Okay, so our integral over C of y cubed dx plus x cubed plus 3xy squared dy, where C is the path from 0, 0 to 0, 1 along y equal to x cubed, and from 1 to 1 to 0 to 0 to 0, 0, back along y equal to x. Okay? All right, so what's this region look like? Well, first of all, I want you to notice that this is not a conservative field. The derivative of y cubed with respect to y would be 3y squared. The derivative of x cubed plus 3xy squared with respect to x would be 3x squared plus 3y squared. So this does not have a potential function. If it did, and we integrated around a closed curve, we would get 0, as we saw in the last section. But this is not a conservative field, and that is why we are using Green's theorem to calculate this. Okay? All right, so let's get an idea of what our region here looks like. Okay. So the points in question are going to be 0, 0, and 1, 1. We first are going to get there from 0, 0 to 1, 1 along the curve y equal to x cubed. So that's going to look like this. Okay, so we're coming this direction. And then we're going to come right back down the line y equal to x to get back to 0. Okay, so there's the point 1, 1, 0, 0. Okay, so we are going in a counterclockwise motion around this curve, and our region R is smooth and simply connected. Sorry, the curve is piecewise smooth, and our region R is simply connected. So then what we're going to have to do is we're going to have to integrate over this curve C. Okay, m is y cubed dx plus n is x cubed plus 3xy squared dy. Okay, but according to Green's theorem, this is going to be equal to the double integral, over r of 3x squared plus 3y squared minus 3y squared dA. Okay, and we do get some lovely cancellation here. So this is going to come out to be the double integral over r of 3x squared dA. All right, so we've got to set this up as we would have done way back whenever we were just setting up to find areas and things, right? So we need to figure out what's bounding y and what's bounding x here. So this one looks like it'd be pretty easy to bound our region vertically, because at the top of the region we always have y equal to x, and at the bottom of the region we always have y equal to x cubed. So this is going to be equal to the integral, and I'm going to integrate dy dx, 3x squared. So y is going to be going from x cubed at the bottom of the region to x at the top of the region. And then once I've bounded myself vertically with y, I look and I see, well, x is just running from 0 to 1. So remember, we have to have constants here on the outside edges. And then we just integrate this as we would have always integrated it. So this is our integral from 0 to 1 of 3x squared y evaluated from x cubed to x dx. Okay, so these are y values, remember, we're plugging in for y. So that's the integral from 0 to y of 3x squared times x minus x cubed dx. Simplifying, we get 3x cubed minus 3x to the 5th dx. Integrate. So this becomes 3/4 x to the 4th minus 3/6 or 1/2 x to the 6th evaluated from 0 to 1. So at 1, that's going to be 3/4 minus 1/2 minus at 0, it's 0 minus 0. So this is just going to be 3/4 minus 2/4 is 1/4. Okay, let's have another example. All right, suppose we have a vector field f of xy given by y cubed in the I direction. That's a cube. There we go. Y cubed in the I direction plus x squared plus 3xy squared in the j direction. Okay, and suppose we have a particle travel once counterclockwise around a circle of radius 3. So it travels once counterclockwise around a circle of radius 3. Let's use Green's theorem to calculate the work done on the particle. Done on the particle by the vector field. Okay, so we've got our circle of radius 3. So that's going to be y squared plus x squared is equal to 3 squared. So we've got y squared plus x squared. Nope, there it is. Y squared plus x squared equal to 9. So that's our circle. So since we're going around a circle, it might be best if we did this in polar coordinates. So if we need that, that's r squared is equal to 9. Okay, so we are going to need to know our partial derivatives. So m is equal to y cubed. N is equal to x squared plus 3xy squared. So the partial of m with respect to y is 3y squared. Partial of n with respect to x is going to be equal to 2x plus 3y squared. Okay, so it is not a conservative field, so we cannot use, it's not going to be integrated nicely like it was in the previous section with the conservative fields, giving us those very nice fundamental theorem of line integrals and all that fun jazzy jazz. So we are going to have to use Green's theorem here, which we can do because we are on a closed curve, we are moving counterclockwise, and we do have a smooth, simple connected region. I keep saying smooth. We have a simply connected region R. C is smooth, so we're going to go there. Okay, so we can go ahead and get this thing set up. So our integral over C of y cubed dx plus x squared plus 3xy squared dy is just going to be equal to the double integral over our region R of 2x plus 3y squared minus 3y squared dA. Okay, so once again, this turned out lovely. We do get some beautiful cancellation. So this is going to be equal to the integral over our region R of 2x dA. Okay, so our region R is bounded below by, let's see here. Oh, I mentioned earlier, we should probably do polar coordinates because it is going around in a circle, so I'm going to do that. I'm going to use this in polar coordinates. So our lower boundary is R equal to 0, and our upper boundary is r equal to 3. So our radius of the circle is going from 0 to 3, so that's how we're getting from the origin to each point on our circle. Then the theta is going from 0 to 2 pi. Okay, and then we've got 2x, but x is of course our cosine of theta, and then r dr d theta is dA. So there it is, a standard double integral. We've been doing these for a while now. So this is going to be the integral from 0 to 2 pi of 2r squared cosine theta. Oops. So it's the integral from 0 to 2 pi of the integral from 0 to 3, there we go, of 2r squared cosine theta integrated with respect to r and then with theta. Integrating with respect to r, we get the integral from 0 to 2 pi of, so we add 1 and divide, 2/3 r cubed cosine of theta, evaluated from 0 to 3 d theta. Okay, so that's the integral from 0 to 2 pi of 2/3 times 3 cubed is 27 minus 0 cubed is 0 times cosine of theta integrated with respect to theta. So 27 divided by 3 is 9, so this is going to be 18 times the integral from 0 to 2 pi of cosine of theta d theta, so that's going to be sine theta. So 16 sine theta evaluated from 0 to 2 pi. So if we do that, what do we get? We get 0. Just 0. But that's not right, right? So that's going to be 18. Where did I get? I can't read my own writing. That's where. That's supposed to be 18, folks, not 16. So this is going to be equal to 18 times 0 minus 0, which is 0, but that's not right. That's not what we're looking for. The problem is that cosine of theta is an even function. So if you look at cosine of theta, it starts here at 1, comes down, and then comes back up. It's an even function. The area above the curve is equal to the area, above the x-axis is equal to the area below the x-axis. So really what we need to do is find just part of this, and then we can multiply that by 4. So we don't want to do this. That's not working out for us. What we get then is we say, okay, well, this is 18 times, well, we could just do times 2 and do it from 0 to pi, right? So this is going to be, what did I just say? Hang on one second. No, 4. That's what we talked about. Okay, so we're going to multiply by 4 and integrate this from 0 to pi over 2 of cosine of theta d theta. So then what we end up with is 18 times 4 times sine of theta evaluated from 0 to pi over 2. So that's going to be 18 times 4, which is going to be 80 minus 8. It's going to be 72 times sine of pi over 2 is 1, sine of 0 is 0, so this is equal to 72. Okay, so that's Green's theorem in a nutshell. There is one more theorem here I'll share with you from our book. It is the line integral for area. All right, so here, if R is a plane region bounded by a piecewise smooth simple closed curve C oriented counterclockwise, then the area of R is given by. So in other words, if all of Green's theorem's conditions are met, we have A is equal to 1/2 times the integral over our curve C of x dy minus y dx. Okay, so if you're looking for the area of a region, we can find that here. And again, this is a simple connected region, so this is for R, simple connected region. Okay, this is the area of this region R, where C is oriented counterclockwise around the region. Okay, so all the conditions of Green's theorem here, and that's going to be your area. All right, guys, that's it for this one. If you have any questions, as always, please let me know.